Hello, my name is Dr. Leo Yvonne Alcorn. I'm a postdoc here at University of Toronto, and I study galaxy clusters. JWST is the newest launched space telescope. It launched on December 25th, 2021. Its mirrors are made of beryllium and coated in gold, which better reflect infrared light. In contrast to Hubble looked at optical light, and JWST looks at infrared light. I've been hearing about JWST since before I became an astronomer, when I was in high school. And it's been a long time coming. So every astronomer that I know is just thrilled that it's finally up and in orbit at Lagrange point 2. JWST's first released science image was, much to my happiness, galaxy cluster SMACS 0723, which is located around 4.6 billion light years away. So that means that we're looking 4.6 billion years in the past. This cluster was observed by NIRCam, MIRI, and NIRISS. The image that you're familiar with was taken with NIRCam, which observes in the near-infrared. It was also observed by MIRI, which observes in the mid-infrared. Best of all, every galaxy in that image has a spectrum taken of it by NIRISS. So all of my friends were very happy to see every single galaxy had a spectrum taken, which allows us to determine how far away the galaxy is and what it's made of. The seeds of galaxy clusters are dark matter clumps, and galaxies are gravitationally attracted to these clumps, to the point that most of the mass of a galaxy cluster is actually dark matter. Dark matter doesn't interact with any other matter except gravitationally, and additionally, it self-gravitates. So when there's a little seed of dark matter, more and more dark matter becomes attracted to that seed, forming an initial dark matter halo. Galaxies fall toward this dark matter halo, and it forms these huge galaxy clusters of hundreds to thousands of galaxies. Dark matter holds these clusters together, just like it holds the rest of the universe together. We also notice that in local clusters, galaxies look very different from galaxies that are not in a galaxy cluster. Galaxies that are in clusters tend to appear redder and have older stellar populations. They also appear to be more elliptical rather than disk-like, like our own Milky Way. An area of active research is how galaxy clusters stop star formation, and JWST will help us learn this. Some of these galaxies are curved because they're subject to a phenomenon called gravitational lensing. Just as an aside, gravitational lensing is actually the phenomenon that inspired me to go into astronomy. Gravitational lensing is a consequence of Einstein's theory of general relativity. Galaxy clusters are so massive, galaxy clusters like SMACS 0723, they're so massive that they literally warp space-time around them. So light bends around these galaxy clusters, forming multiple images as well as stretched and elongated images. So if you look at SMACS 0723, you'll notice that around the edges of the galaxy cluster, there is these streaks. These are lensed galaxies. These galaxies are not actually located at the edges of the cluster. Instead, they are galaxies that are very, very far away behind the cluster, some of them up to 13 billion light years away. The great thing about gravitational lensing is that it acts like a literal lens. So these galaxies are not only warped and elongated, they're also magnified. This is a huge help for astronomers that look at high redshift galaxies, because we have these magnified galaxies. Usually when galaxies are that far away, we can barely see anything about their internal structure. But when they're lensed, we can actually look at their internal structure. I actually have a galaxy cluster like SMACS 0723 tattooed on me. So here's the galaxies in the background that have been lensed. Here's the lensing cluster. And now let's see what happens when we add a little mass to the system. Now that's what I call mastrophysics. JWST has been a long time in the works, and astronomers have been very excited for it to be launched because it's greatly improved our understanding of galaxies and galaxy clusters. In this particular instance, JWST looks at near-infrared light. As galaxies get farther and farther away, they start moving faster and faster. As they move faster and faster, the light is redshifted, or it's pulled apart thanks to the Doppler effect. So when we look at galaxies that are farther away, more of their light is in the near-infrared. So when we look at a galaxy cluster using JWST, we can actually look at more of its optical characteristics in the near-infrared. Observations taken by MIRI are very useful because most of the dust of a galaxy is located in the mid-infrared. So we can learn a lot about the dust in these systems by looking at MIRI. Additionally, each galaxy was observed by NIRISS, a spectrograph on the James Webb Space Telescope. When astronomers looked at all of these galaxies that were observed using the spectrograph, they noticed that there was a galaxy located at a distance of 13 billion years away. This is very hard to observe using Hubble or ground-based telescopes, and it really shows us just how important something like JWST is, that we're able to look at something so distant and see the features that we see in the spectrum just so clearly. Hubble is a fantastic telescope. As you can see, I also have another tattoo of Hubble. But a Hubble doesn't have as large of a light collecting field. Its diameter is much smaller, on the order of 2 meters, in comparison to JWST, which has a diameter of 6.5 meters. This can make a huge difference because it allows us to see fainter and smaller objects. One of the stated goals of JWST is to learn about the first galaxies. And with that, we'll learn about the first galaxy clusters. Thanks to JWST's coverage of near and mid-infrared light, we'll be able to look at more and more distant galaxies up until the universe was very, very young, a little bit more than 13 billion light years away. So we'd be looking at galaxies in the early universe. As we look further and further back in time, we'll be able to start to see these seeds of structure that form galaxy clusters. So we'll be able to look at very, very distant clusters and learn more about how these galaxy clusters form at the earliest times. In addition, we'll be able to learn more about how galaxy clusters stop star formation. This can be very useful because we'll be looking at older stellar populations and galaxies that are going through their transition between star forming and non-star forming. We can study how dust and elements that form even our own Earth start to form in these galaxies as well by looking at the spectra of these galaxies with NIRISS. There are many more observations of galaxy clusters just like SMACS 0723 that are going to be observed. As we observe more, we're going to learn more and more about how these fascinating structures form.